Let's use some of the results we just developed to solve some applications of extrema. In example 1, we have a rectangular box that is resting in the xy plane with one vertex at the origin. The opposite vertex is supposed to lie in the plane 6x plus 4y plus 3z equals to 24, as shown below. The question is, what is the maximum possible volume of the box? Well, we know that the volume of a box is length times width times height. The fact that one vertex lies at the origin, and another one has to lie on this plane, so that point x comma y comma z, which lies in the plane, that x value would be the length, the y value would be the width. So we have x, this would be y, and then the height would be given by the z coordinate. So the volume here is going to be x times y times z. Obviously, if there was no constraints, you would just choose x, y, and z larger and larger, and we would continue to get a larger volume. However, our constraint equation is that the point x comma y comma z has to be on the plane 6x plus 4y plus 3z equals to 24. So we want to maximize z equals x times y times z subject to 6x plus 4y plus 3z equals 24. One of the things we can do to reduce this to a function of two variables is let's take our constraint equation and solve it for z. 3z would be equal to 24 minus 6x minus 4y, and then if we multiply everything by a third, that will clear off the z, make it a z to the 1z. We have 24 minus 6x minus 4y times a third would be equal to z. So we can go ahead and plug that into our volume expression to find that the volume as a function of x and y is going to be equal to, so wherever I see a z, I'm going to put this. It's x times y times 1/3 24 minus 6x minus 4y, or I'll just keep the 1/3 on the outside. If I distribute the x and the y in, we get 24xy minus 6x squared y minus 4x y squared. And we want to maximize this. Let's go ahead and see if we can find our critical points. The critical points come from wherever the partial with respect to x and the partial with respect to y of v would be both equal to 0. We won't get any other of critical points from where either vx or vy would be undefined. We'll see here in a minute that both vx and vy are going to be polynomials, and so they will be defined everywhere. So the only source of potential critical points for this problem comes from where vx is equal to 0 and also from where vy would be equal to 0. If we take the partial with respect to x, we would see that vx is going to be equal to, we have a constant multiple of 1/3. So when we take the partial with respect to x, we're holding y constant. This is going to give us 24y minus 12xy minus 4y squared, which we can rewrite a little bit more. Each term on the inside is a common factor of y, so we can pull that y out. So we would have y divided by 3 times 24 minus 12x minus 4y. If we set this equal to 0, we have y divided by 3 equal to 0. 24 minus 12x minus 4y equals to 0. This one would tell us that y equals to 0. And then this expression here, this would give us something in the variable y. I could take this and solve for y, get y by itself, and we would see that we would get, add 4y to both sides and then divide by 4, we would get that y would be equal to 6 minus 3x. And we'll come back to this in a minute. If we go ahead and find the partial with respect to y, the partial of v with respect to y, here's my function v. That's going to be 1/3. We're holding x constant now and differentiating with respect to y. So we're going to get 24x minus 6x squared minus 8xy if I can squeeze that in. Let me just try that again. Come back. There we are. Vy we said was 1/3. 24x minus 6x squared minus 8xy. Every term that belongs to Vy has a common factor of x in it, so let's pull the x out. We have x over 3 times 24 minus 6x minus 8y. If we set Vy equal to 0, we get x over 3 equals to 0, or 24 minus 6x minus 8y equals to 0. This first one would imply that x equals to 0. And then from there, we have this expression here, 24 minus 6x minus 8y equals to 0. So what do we know here? So first of all, one critical point is going to be if y is equal to 0. So remember, both of these two conditions, so this condition and this condition had to be satisfied at the same time. So one ordered pair that will work is going to be x equals to 0 and y equals to 0. So if both x are 0 and y equals to 0, then that would work. Coming from this piece and this piece. However, we could have y equals to 0 and this part for the other function, which would give us 0. And then if I plug 0 in for y here, that would give us 24 minus 6x equals to 0, which would give us an x value of 4. So we also get a critical point for 0. On the other hand, if we work with this piece and this piece, if x is 0, then I would plug 0 into here, and we would get y equals to 6. So that would be 0, 6. And then the other thing is if I take these two equations here simultaneously, 6 minus 3x equals to y, 24 minus 6x minus 8y equals to 0. You could solve them like a system of equations. In particular, this one's already solved for y, so you could do substitution. This would give us yet another critical point. I'm not going to show the work for that, but that would be 4/3, 2. So altogether, we get these 4 critical points. We now would want to see which ones would potentially yield a maximum. Notice that if we go back to the volume formula, if any of these coordinates have a 0 in them, then that would produce a volume of 0. So certainly none of those could produce the maximum volume, because those wouldn't even produce a box at all. It'd be a degenerate box. Okay. So we have one candidate here. Let's investigate this one, this 4/3, 2. To do that, what we would want to do is check our d value from the last section. So to see whether we have a maximum, a relative max, or relative min, we need to check this value d. The formula for that, if you recall, it was the partial, double partial with respect to x, times the second partial with respect to y minus the mixed partial squared evaluated at the expression. If I go ahead and calculate the second partial with respect to x, keep the y constant, so this would be y over 3 times negative 12, which is simply negative 4y. If we do the second partial with respect to y, keep the x constant, this would be x over 3 times negative 8, which would be negative 8/3 x. And then we need the mixed partial. So if I go back to the partial with respect to x, and I do the partial of it with respect to y, I'm taking this one here, taking the partial with respect to y. It would be more convenient if I actually distribute the y over 3 in first, so I don't have to get caught up in using a product rule. So let me just come up here. I'm going to rewrite Vx first. This would be y over 3 times 24 is 8y, minus y over 3 times negative 12x would be a negative 4xy, and then y over 3 times a negative 4y would be a negative 4/3 y squared. And now in this form, this is a good form to go ahead and take the partial with respect to y. If I hold x constant, then the partial with respect to y would be 8 minus 4x minus 8/3 y. You would then want to go ahead and evaluate these at this point, 4/3 comma 2. So d evaluated at 4/3 comma 2. This is going to be equal to Vxx, which is negative 4y. So that's going to be negative 4 times 2 times Vyy. That's the negative 8/3 x. That's going to be negative 8/3 times positive 4/3. Minus Vxy squared. So you'd have to put the pair 4/3 comma 2 into this expression right, where is it? Right here. That would be 8 minus 4 times 4/3 minus 8/3 times y, which was 2. I'll leave this computational part of it up to you, but if you calculate d, d will actually end up being equal to 64/3, which is greater than 0. So this is the case where d is greater than 0, and in addition, what we would also need to know is the sign of Vxx. Vxx was this part here, that was negative 8, which is less than 0. Because d is greater than 0 and Vxx is less than 0, the second partials test would tell us that this would produce a maximum. So we have a maximum at 4/3 comma 2. The directions weren't simply to find the coordinates of it. We were actually asked and tasked with finding the maximum volume of the box. I deleted my v function, but if you go ahead and plug this back in, the volume that would correspond to 4/3 comma 2 that would be equal to, I have it written down off the side here, it's going to be 1/3 times 24 times x times y minus 6 times x squared times y and then minus 4x times y squared. If you compute this, this will give us a volume equal to 64/9 cubic units.